He's the student of this session. He's Zhou and comes from the University of Bristol. He will talk about a longitudinal study of aerosol emissions for human participants and the correlation with their emissions and commensal bacteria during speech. Thank you very much.
Thank you. Hi, good morning. I'm Nan, and today I'm presenting my CDT project, AirMap, the Aerosol Investigation and Respiratory Monitoring Assessment project. Let's start with some basics. So first, there are three routes of disease transmission: direct contact, droplet spread, and airborne aerosols. For airborne aerosols, they are particles ranging from 1 to 10 micrometers, travel long distances, and can be easily masked by indoor background. And for exhaled aerosols, there are generally three generation modes: the bronchiolar fluid film burst, the laryngeal mode, and the oral cavity mode. So, to measure how much particles a patient emits, the golden standard is in an ultra-clean ventilation theatre. In a UCV theatre, the background is almost zero. So what we are detecting is all coming from the patient himself. However, the UCV theatres are expensive and hard to get access to. And it is almost impossible for us to recruit 50 people and let them visit the UCV theatre 6 times. So the central question behind my work is, can we push the background low enough in an ordinary room to make it behave like an UCV theatre? So the aim of my part 1 is, can we develop and validate a novel method for respiratory aerosol quantification outside of an ultra-clean theatre? That's how we address this problem. To start with, the air purifications. We place different numbers of purifiers in the CDT room around the sampling people, and to minimize the background aerosols. And second is the low resistance filters. So the low resistance filters is fitted to the CPAP mask and connected to the APS by a 1 meter conductive silicone tubing. And the participants are required to do a sequence of standardized respiratory activities, including tidal breathing, deep breathing, and conversational and loud vocalizations. So, does the purification actually work? We had found that by using 10 purifiers, we are able to reduce the background aerosols to 1% within 4 minutes. And why don't we have purifiers more than 10? So believe me, you won't want to stay in a room with 10 purifiers roaming around you. It's really noisy. And seen from the figure at the right, having 10 purifiers, the measured ACH is actually lower than the nominal ACH, meaning that having the benefits of more than 10 purifiers is actually quite limited. And we suspect there might be infiltration of particles inside the room, like particles from the corridor or something, because of too many filters. So that's why we finally decided to use 10 purifiers in that room. And does the filters really work? So here I present 3 different environments using all the same setups. The CDT30 refers to the CDT room without any purifications. And the CDT clean refers to the CDT room with 10 air purifiers working. And the UCV theatre is just UCV theatre. So we found that the room cleaning alone is insufficient for tidal breathing, especially because it's so low in its concentration. And from left to right, there are 0 filter, 1, 3, 5, and 7. And we found that 3 and 5 filters is really our sweet spot. And any number beyond this might just cause like increased breathing resistance that will alter, like increase the number of aerosol emitted for the participants. So finally, we choose 5 filters in 2 legs as our final setup. Finally, we validate our air map data with all previous published data sets. And we found out our data set is really comparable to those published data sets in UCV theaters. And noticeably, the data acquired by Nava, which used a setup with mask plus single filter in a non-UCV environment, is significantly higher than our result, which makes sense because we have tested that one filter with the mask can be easily overwhelmed by background aerosols, and it's very susceptible to high flow rate. So it can make sense that they are higher than us, especially in tidal and deep breathing. Once we validated our method, now it's time to move on to part 2, the longitudinal study. We have recruited 44 participants and measured them on day 0, 1, 7, 14, and 28. And 30 of them returned for 6-month follow-up, luckily. And we have in total measured up to 6,500 minutes of respiratory aerosol sampling data. And that is so far the largest data set as far as I know. Great, so the aims for part 2 is, do high emitters stay high emitters? And do people emit the same particle size distribution of particles? And the answer is yes. So here are the box plot. So it's colored based on the ranking on day 1. And seeing from this data, so the high emitters on day 1 remain high emitters throughout 180 days. And the lowest emitters stayed low within 6 months as well. And next, we did some statistical analysis. So the intra-class correlation coefficient, which is the standard statistical test for bioaerosol stability. And we found that the deep breathing, conversational, and loud vocalization stayed quite consistent. With the tidal breathing be a bit lower, which makes sense as well, because tidal breathing is so low, it's in its concentration, and is most easily affected by any noise. So now we have showed that the aerosol number concentration is consistent. But we want to ask another question. So what we measured, does it actually relate to something that is biologically meaningful? And that's where the imagine comes in. And this study is conducted by the amazing Patricia, who is also here today. And she got a post upstairs. Make sure you talk to her if you're interested. So what Patricia and her team did is they used a HEPA filtered isolator, which create a closed clean chamber. And then she placed settle plates, slit sampler, and Anderson impactor inside the chamber, which can both capture droplets or aerosols of different sizes. And they used the commensal bacteria as a proxy for pathogen dispersal. And we got the privilege to pair our air map data with the imagine data, and we can compare the rank of high emitters on both studies. And here's what I found. So we found that the super emitter rankings agree across both studies. And especially for Anderson impactor, which was statistically positively associated with our air map. So the high emitters are consistent between the two methods, which means that the participant emit the most number of particles can also emit the most number of bacteria. And this is done for 25 overlapping participants. In conclusion, we have successfully validated the CPAP mask plus 5 filters method. And our longitudinal study indicates that the respiratory aerosol is stable among individuals over time. And the bacterial colony counts really correlated positively with aerosol emissions. For our future work, we want to extend AirMap to more different aspects. First, of course, deeper imaging comparisons, and I look forward to more collaborations between Patricia. And secondly, size distribution analysis. We want to obtain comparable distributions per individual, not as a cohort averages. So now we actually have got enough data to show that the size distribution of a single individual is constant over days. And the final thing is the hygroscopicity measurement. So there are two nozzles on the mask. Now we only use one of them and the other is closed. Where we can connect two tubes of these two nozzles and varying one RH and just compare these two. And finally, here are the acknowledgements. I really want to thank my supervisor, Jonathan Wright, and my TVS supervisor, Matthew Jones, Anita McGogan, and my two master students, Tobias and Natalie, and also my supervisor, Andy Shrimpton, and his sixth form student, Daniel, and all my wonderful teammates from BARC, of course. And today I've seen many of my volunteers on site. So last but not least, thank you from the bottom of my heart for being an air mapper. Thank you very much.
And then for this next talk, we have time for some questions. Yeah.
Yeah, that's some really interesting stuff, that. And regarding the business of super emitters, what's the current prevailing wisdom on what the physiological reason for that is? I mean, why are some people emitting so much more particles than others?
Oh yeah, we did do a lot of investigations into different factors like age, sex, BMI, races, and so honestly, we only found the age to be the only statistically significant factors that affecting the aerosol emission. However, my supervisor is really debating me regarding this because we have a such.
Supervisor used to voting.
Oh yeah, because we have such a young cohort, so the age distribution is quite screwed. That's why I'm not sure. That's why I'm not showing any of the data here. So for next stage, we are planning to recruit more mature participants. Yeah. Thank you for asking. Yeah.
Great talk. Bill from University of Manchester 407. I had a question about kind of identifying that 500 sweet spot, and maybe you covered this in some data points in the visualization you showed. But have you accounted for different room geometries and different orientations of the various filter devices?
That's a really good question. So I think that needs some CFD models. Yeah, but right now we are just place the 10 purifiers evenly in that room. Yeah.
How do you maybe to use the question, how do you determine what exactly?
Oh, just 4 at the corners, 4 at the middles, and 2 anywhere. So just around the room. Yeah.
Thank you very much.
No worries.
I'm subscribed to Bath. Thanks, very nice talk. Sorry if I missed this. Were the people who consistently gave more aerosol from the loud ventilation the same ones that consistently gave more droplets from deep breathing, or did they not?
Oh, that's a great question. So I've also have a figure. So now for the box plot I'm showing here, it's color gradient based on day one of the individual activities. I've another figure that's so the hopeful color gradient is based on the tidal breathing on day one. And we found that there are a lot of like jumpy points, but the overall trend is still similar. So I would be interested to do on the deep breathing. I think that's actually during our last meeting with Jonathan, and we actually did discuss about that and want to color gradient on the day one of deep breathing for all 4 activities. I'll be excited to see the results there.
I guess all you past participants were healthy participants, and we
Yes.
don't have any infected people. But then you think that the results would be better if you would have infected people by viruses and instead of looking at bacteria, you would look at virus that we can have a translation between healthy to non-healthy and bacteria. So are you going to do a bit more work on maybe trying to work well, maybe not infect, well, maybe infected, but then, see if there is also some kind of trend?
That's a great question. Thank you very much. Yeah, that's what we're looking into in the future. So now under our current ethical form, we're only able to recruit healthy participants. But if you check the Navas paper, they are comparing healthy and non-healthy participants, and they currently find no significant difference between these two cohorts. However, I would say their method is not that reliable as us. So yeah, we're looking forward to using like our method, our setup to do quite similar cohort comparisons.
Okay, thank you very much. Now we have to start. If you have more questions, you can approach to the students, please. A big applause to all the